Hi, hello everyone, and welcome to this video where we will be doing this. What we're going to do this time is view matrix or look at matrix. But before we do all of that, let's just get rid of well, this flickering and all of this stuff, which we're not going to need. So I can get rid of this here in our draw method where we're updating our matrices, right? In this 4 to 10 loop, let's get rid of that. We're just going to draw one instance of our cube, and there it is here. So then let's modify some other stuff. So buffer size, we cannot change that because our array size is kind of hard coded in shader, right? Here it's 100. So let's not change the size. But what we can change is basically this. We might not even need transforms here. We can just say here transform matrix. We're going to need it. So we're going to place our cube at position 003, and then we're going to update our transform matrix, and here we don't need any byte offset, so we can leave this and actually just place 0. Transforms, we don't need it, so we're just going to update here, and we're probably good. I just need some formatting fixes. If I save, we have a cube at position 003. Okay, cool. Also, we're probably going to need some methods. So yeah, we're probably going to need some methods and the whole new vector3 class that I have created. So please just check in the description of the video GitHub code. It's simple class similar to our vector2. We just have additional z component here. So all of this you already know, right? Get x. And then I needed some methods which will be length of a vector. So I'm going to explain that. We're going to need subtract, all right? Normalize vector, going to explain that as well as we go. Cross vector of two vectors. So same, and then the dot product as well. So we're going to need those operations, and then in our matrix class, in our matrix class, we're just going to need transpose operation. What transpose does is just reverts rows and columns. So you can copy those from the GitHub. It will be in the end video, so part 10 or 11, I don't know anymore. But you can just copy them and then you're good to go. If you're missing something, just check vec3 and matrix 4x4 class. Okay, so to actually view matrix or look at matrix. So let's first just define our look at matrix, and then we can discuss it. So it's going to be public static, and we can just call this look at. And here we already need vector 3 for I. So we're going to have parameter called target. And then we're going to have parameter called up. And there are already some suggestions, so I'm just going to remove this for now, because we're not going to need it. Right now, I'm not even sure if those are good. Usually those suggestions, they might come. It could be like that here, what is it called? GitHub Copilot in my case. It might be that it copies the met operations from the GL, and that doesn't necessarily have to be correct in some cases. For look at matrix, it might as well, but sometimes you work in right-hand coordinate system, sometimes left-handed. We're here in left-handed coordinate system, so we're going to do matrix for that. But let's see, what am I looking for? I'm looking for this. So we're basically going to start with new matrix, const matrix is new matrix 4x4, and I believe it's already the identity by default. So we can just return it, and then we can let's now just quickly discuss what these parameters are. So I'm here on drawing board, and we can imagine our coordinate system, and for simplicity I'm just going to say here z and y, and you can imagine x going somewhere here, right? Here is negative x, whatever. You can imagine that it's 3D. So we have this first parameter, which is called I, right? And then the second target. And then the third one is called up. Up is quite simple. So I'm just going to up. So I'm just going to quickly discuss what app is going to be. It's usually going to be 0, 1, 0, and it's going to define our app up, basically up vector, and it's almost always going to be 0, 1, 0, unless you want to work with some weird spread. So just pass 0, 1, 0 by default and forget about it. We're going to need it for orientation of the camera. So if you imagine our camera being here, right, and looking towards the z-axis as it's looking right now, right, you know this buffer thing, sorry, normals device coordinates, where we said, okay, our z space goes from 0 to 1, right, and the camera is already looking by default at z, so we're in left-handed coordinate system. It's left-handed when z is kind of pointing towards the screen, and I defines where we want our camera to be. So right now it's at position 0, 0, 0, but we could move it, right? We could say it's at, let's add the negative here. We can say as well, okay, let's place our camera here. So I'm going to say that this is maybe, sorry, not x we're not touching. So we're going to have 3 in y and maybe -3 in z. So we can place our camera here, for example, and then we have this target parameter, and target says where the camera is pointing at, right? So if we say our target is somewhere over here, let's say that target is 0, 1, 0. So when we define a target, it's actually going to orient our camera, right? So our camera is going to be oriented towards the target. So that's what target defines. So basically, and this up, like I mentioned, always just say 0, 1, 0 or y direction. So it's going to define up vector for our camera. So if you imagine our camera here, maybe, right, at some position here, it's at some, let's say, yeah, this is close like 0, 2, and then 5 maybe, and we can say it's looking at, for example, 0, 0, 0. All right, so that's easy. So now we have to solve actually for those parameters, and we're going to start with I, because I is super easy. So we can just start with I. So if we want, actually let's go to code, and then we can discuss it. So for I, we can just go to our main, and we're going to create first lookAt camera, and then we're going to do stuff with it. So we're going to need, we already have perspective. So here I'm just going to get rid of this software effect, it's not important for now. So I'm just going to say view, and here I'm going to say matrix 4x4 lookAt, and then what do we want to do? So let's say that we want to move our camera a bit up at position 0, 3, 0. So our target is not important for now, but I'm going to place it at 0, 0, 3 because here I placed I placed our cube at position 0, 0, 3, and we want to take a look at that cube. For now it's not important, and here I'm, like I mentioned, 0, 1, 0 for up. It means that y is up direction, and that's what we need. So we're at somewhere up. So we're not done yet. So I'm just going to move this perspective outside, and I'm just going to call this perspective. So okay, this is broken. So just to discuss one thing before we go on, because I completely forgot about it. So I haven't even talked about our transformation. So I talked about view camera, but also some stuff that we need to know. So we had our, what I'm going to call vector or vertex. You can call it vertex as well. So it's defined, usually our simplest primitive that we can draw that's not a line or a point is a triangle, right? So it has some vertex, let's say vertex 1, vertex 2, and vertex 3. So next important thing that we had to do is some, call it model matrix. I think we called it transform matrix. You can also use model matrix. It's probably more correct as a model matrix, but we called it transform matrix. Anyway, it's not important. So what did this do, right? So basically, if we imagine our rectangle here with model matrix, we could translate it to some other position. We could scale it, right, so that it's bigger, but we could also rotate it, right? So let's say that this is rotated somehow. So that's what our model matrix did. So then we skipped this step, which is called view, and I'm going to get back to it. But then we had perspective. So our transformations are defined like view, right? Our vertex, sorry, not view, vertex, times model matrix, times view matrix. We're going to skip that for now, and then times perspective matrix. It's in your shader, it's reversed, because we're actually, when you're using WebGPU, you're in column major space. So the operations need to be reversed. So for us, it was it's now going to be, sorry, perspective, view, model, and then here. So this is how it looks in our shader, because we're in column major. Here, usually you're going to see, when you read a book or something, you're going to see row major order. Anyway, it's not important, but then we also had our perspective. And what did this do, right? If we imagine we had our triangle, we said that, let's say that we could affect the field of view, right? So we were affecting field of view, and what was else? So we could say how far we can look into, right? So we were doing this. We mentioned that we have 1 to 0 space for our coordinates, but we could also, we usually said that for our perspective matrix, right, for 3D matrix at least, we change that space to 0.01 with some linear algebra to let's say space 100. So our perspective matrix basically defined our field of view and how far do we see. But the view matrix, so the view matrix kind of defines, right, where our camera is looking at. It will define up and right vector for our camera, so right, forward, and up. But it also defines where it is in space. So let's say maybe it's here, maybe it's here, right? So it kind of defines where it is to space and where it's looking at. So that's the view matrix part. So we're going to deal with it now. So regarding math, so I mentioned that we just need to multiply it, and I also mentioned just now, since we're in column major order, we actually do perspective times view. Otherwise, if you read some math books, it might be a bit, it might be reversed. But we can just say here perspective times view, and nothing is changed, right? Because like I mentioned with perspective, we were changing the field of view. If I increase it, it's smaller. That affects our field of view. But here we want to affect where our camera is. So we want to move our camera up. So our cube might be a bit down. Okay. So how do we do that? So with our eye, let's say, where are you, matrix? So we had our eye. We can create first, I'm going to call it translate. And you're going to see our lookAt matrix is going to have translation part and rotation part. Translation part says, okay, where we are in the world, and rotation part is going to say, okay, where are we looking at? So for this part, I could just say translate. And here it gives good suggestion, but I'm just going to use I so that I can explain it as well. And so here we don't see anything, which is probably because I went too far up. So let's just place it at 1. Okay, cool. So I here said 0, 1, 0, and that's supposed to move camera up, but our cube went up, so it means our camera is below the cube. We want to be above the cube. And I did that on purpose so that I can explain it, right? So if you're looking here, so I haven't drawn anything yet, but let's imagine this case. So we're going to have our y, and then we're going to have our z, right? And we're looking towards the z, right? We're in left-handed coordinate system. So if we imagine our camera being here, right? And our cube, I mentioned that it's some position 003. And our camera is at 000 right And I kind of wanted to move it up, right, at some position 0, 0. But I moved it up, and logical confusion would be logical conclusion, not confusion, would be that our cube is below our camera, but right now that's not the case, right? It's above, and the reason for that is, well, basically, as you remember, I mentioned that we're always that our device coordinates, right, -1 to 1, 1, -1, and then for z, right, it was 0 to 1. Similar to how we had to do for perspective matrix, we have to reverse this, right? We cannot just do it like this because our device coordinates are what they are, and we're actually not moving the camera around. We just kind of model it like that, but when we model the final matrix, right, of our camera, we actually want to move these vertices into camera space. So what do we need to do for this to actually appear as below the camera? Well, we actually need to inverse what we had, right, for the camera. So if we inverse this, right, this -1, cube translation is going to go at 0, 1, 3. So we just, whatever our eye is, we just need to inverse it, and then the cube is finally moved. So you actually move these vertices around, right, when you talk about what's actually happening, and it kind of works. So basically we have our translation part, and if we want for our camera to work, we just need to inverse that translation. And the inverse of translation part, all right, I'm just going to quickly do the matrix here. So we have this identity part. Identity part here, I'm just going to say it's 0, sorry, 1, 0, 0, 1, 0, and then here, right, this is identity part, and then we define translation here, and I'm going to show it in code, right? And here we had 1, and this column was also identity. So here it's actually filled with these ones. And in our code, so if we take a look at our translation matrix, right, it's defined here. So in order for the cube to appear as below the camera, we just need to inverse our translation. So inversing translation is really easy. You just say, okay. So we just need to place minus here, and minus here, and we have inversed it. So yeah, super easy, right? So that's going to be the case with UV camera. You just have to inverse your operations. So regarding rotation, so I can say here const rotation, and for rotation I'm just going to do this. Okay, so it did a bunch of stuff here, but actually I'm going to do this new matrix 4x4 rotation set, and then we're going to set these rotations. So I'm just going to pass identity for now, right? So we're already used to it. And then we can say here finally multiply. So I mentioned that the lookAt camera or view camera is defined by two matrices, right? One is for translation, the other is for rotation. Okay, so let's take a look at it here. So we already did translation part. So now regarding rotation, so if we imagine our camera being here, so how is this rotation defined? Well, it's defined by what we called forward vector. It's defined what we call up vector. Come on, up. And then it also has, let's say here it's some right vector. In matrix form, and now mind you, I'm in column major, so you might also see this reversed when you read some book or something. So yeah, so here we're going to have right x, right y, right z, and then 0. Then we're going to have up x, up y, up z, and then 0. And here similar, we're going to have forward x, forward y, forward z, then 0, and then 0, 0, 0, 1. Once you multiply you can actually, you're going to see later we're going to have translation part here, but it needs to be multiplied by this vector. Anyway, it's not important. We have our translation matrix. Sorry, rotation matrix. So how is this going to work? Well, we need to find those vectors, right? And this is why I added those operations to vector, like this cross dot. Sorry, not dot, it's not important for the, but it's normalize is important. So these are going to need to be normal vectors. So what does it mean to be normal vector, right? Well, if we imagine that we have some vector here, 0, 0, 5, if we normalize it, it's going to have length of 1, right? Similarly, here we have some vector that points to 5, 5. If we normalize it, it's not going to be 1, because that's not the length of 1, but it's going to be 0. I think 7 something, and then 0.7 something, right? Because normalization is actually it's 1 square plus 1 squared, and then you get the normal of vector. Not important. Important part is the length of it is 1. So we're going to need it. So how can we find? And the first one that we want to find is forward vector. So how can we find that forward vector? Well, like I mentioned, we have this camera here, and let's say that we're looking at some cube. So we passed first parameter was I, but second one was target, right? So we can say, okay, here is the target, and here is our I. So if we do, right, if we do target minus I, you're going to get a vector that points here, right? And then we just need to normalize it. So let's do simpler example, right? So let's say our camera is at position 0, 0, 1, and our cube, so camera, let's say I, and here let's say target is at position 0, 0, 3. If you do the math, right, if you just say our target, so our 0, 0, 3 minus 0, 0, 1, we get 0, 0, 2 for forward vector, right? This is all forward vector. If we normalize it, we get 0, 0, 1. So yeah, we have this vector here. If we normalize it, it might be actually this length, if we're looking from the eye, right? Okay, cool. So let's just quickly do our forward vector, which is super simple. And so now it's the part where you actually need those methods that I mentioned. So please just copy vector. Actually, you already had to copy vector 3, but let's just say our const forward. So we're going to need to normalize it. We're going to need to subtract I from the target, and then we just need to normalize it. And that's our forward vector, and we can already pass it in. Be mindful, it goes here, right? Because it's the z is the final forward direction, and then forward, come on, z. Cool. It actually moved a bit. Huh, weird. Right? So actually, I'll just do that because I'm curious. What it should be 0, 0. No, it should not be 0, 0, 1 because our camera is up. So that's why it moved a bit. But if we place our camera now at 0, 0, 0, it should work as expected. 0, 0, 0, 0, 0, 1. We're always looking forward. We're just zooming in a bit. Okay, cool. So let's just go up. Okay, so our next vector. I need to find some space here. Our next vector, it can be up vector. And here we need the cross product. So what does the cross product do? So let's say that we have, let's see. Okay, let's say that we have some 0, 1, 0 vector, which is up. Let's say that we have some here I'm just going to use z as I used it before, and if we do cross product of those two vectors, actually it's right should be somewhere here actually, but it's not important. If we do cross product of these two vectors, we're going to get right vector, right? So basically 0 1 0 cross 0 0 1 is going to be equal to 1 0 0, and it also works with non-zero vectors, but they need to be unit vectors, right? So they need to have a length of 1. And the property of cross product is vector that you're going to get is always going to be orthogonal to this vector and this vector in this case, right? It's going to be orthogonal to two vectors. So that's the property of cross product. So we can make use of it in our code. So I'm going to say here in our main. So what did I mention? I mentioned that we can find our right vector. So we can do cross product of our forward and up vectors. So we paste forward vector, right? We paste it here, and then we get right vector. So be mindful, this forward and up, we might need to reverse it. So right now I'm expecting, based on our I and our target, so that this right vector is 1 0 0. So let's just see if it actually is. So I might need to reverse those. Okay, let's see. Right, it's -1, so I'm just going to reverse those. So the thing with the orthogonality, right, is if we have 1 0 here cross come on, is it that hard to write it? Cross 0 0 1, we might get this vector, but if we reverse it, we might get -1 vector, right? Both are orthogonal and both are valid. So it kind of depends on this order. So my advice, instead of just trial and error, try both, and that's probably fine. And last one, we need up, and here up is already used, so I'm just going to call it, well, it can be up. At this point we don't need up anymore, so I'm just going to rewrite up. So it's a cross product of forward and right vector. So let's just try this one as well. It needs to be, if I save it, if I run it, it needs to be 1 0. Actually it doesn't, because it's a bit different, because here we're at position 1 0 1. If I do it again, it's 0 1 0. That's quite all right. So let's go to our main. Sorry, not main. Let's go to our matrix. We have our up vector, and here, since both of these are normalized, it's probably fine if we don't normalize this either. So we can skip that, and then we just need to enter those vectors. So we have up x, up y in the second row, up z, and we have forward x, forward y, forward z, and oh, not forward, right, my bad. When I say forward, I always mean right for some reason. I'm not sure why. And it actually works now. So if I try to move our camera up, that works. If I try to move right, okay, it's good. It's even good. Let's see. If that's all right. But we're not looking quite correctly at the cube yet, right? You should always be pointed at the cube. If I take... No, sorry, my bad. I actually want to go up, and I want to look at the cube, but we're not doing that. And the reason why we're not doing that, similar to what I mentioned in our translation that so yeah, in our translation, if I find it here somewhere, let's try to find it. Our translation, what did we have to do? We had to inverse it, right? We had to inverse our translation. So the same thing we need to do with the rotational part of the matrix, which is defined like this. So we had our right vector, x, right, y, right, z, and then 0. We had up x, up y, up z, and then 0. We had forward x, forward y, forward z, and then 0, and 0, 0, 0, 1. So we need to inverse it. And how can we inverse this rotational part, right? We don't have to worry about this or this. So the inverse of rotational part is actually, we can just do transpose, right? And then if we transpose, our rows and columns are switched. So we have right x, right y, right z. We have up x, up y, up z, and then we have forward x, forward y, forward z, and this stay the same, 0, 0, 0, 0, 0, and that's quite right. So why is this important, right? Well, the same thing that we had here, right? If we wanted to move our cube kinda so that it appears that it's right, we're actually not moving the camera. So we kinda wanted the camera to actually to appear to, like it's going up, but we can't do that, right? We cannot do that. We cannot change the space, so our cube went up. So here it's similar, right? If we say here we have some point, it's not important. If we want to rotate it kinda here, we actually have to do the inverse so that camera sees this. So this is the inverse. And you're going to see this probably a bit later when we do lighting as well. So just remember, if you do the transpose of the rotation, you're going to undo the rotation, kind of. It's going to be important there, but here we just kind of use it to map correctly. So if I go to our what do we need? Matrix 4x4, I can actually say here matrix, and here I have actually added translation as well. So you're kind of going to need to fetch it from the GitHub, because I didn't want to like waste time on this. Not translate, oh my god, transpose. We want to transpose, not translate. So it kind of works now, right? And that's good. That's good. Let's just copy this, and we can now play with it just for testing. So here in row here, it's probably fine. We have our projection view, and we need this thing that updates the projection view, where it is. Not this. It was defined on camera, and camera is already passed to the shader. So okay, let's do that. Let's say some position is 0. And if I start moving camera to the right, is it going to work? Well, obviously we need to increase our position. So we're always looking at our target, which is at 0, 0, 0, and we're moving right. But as we're moving right, we're moving further and further right. So if I do the same for y, and if I do the same for z, cool. Okay, that checks out. Let's just move this here. So if we're going up, we're going up. So our position is working quite correct. But if we change our target, which is now at 0, 0, 3, let's just say plus position. So we're looking, our target is going behind the camera, so that is working as well. So if we do plus minus position, right, we kind of looking in front of the camera, right? So okay, let's just restart it so that I can show it. So as we're decreasing our position, right? So if I restart it, so come on. So right, it's difficult to explain, but basically our camera was here, our cube was here, and it's going behind, right? Because we're actually looking in front of it. So we're kind of going towards the position 0, 0, 0, as we can imagine. Here it was position 0, 0, 3, and as we're rotating, we're actually losing the cube from our side. Okay, that works, and let's try to increase the right target. So we're going to the right. Okay, we can probably conclude that this works as expected. And yeah, that's almost it. I'm just going to add here position because it's kind of cool to see animation. Nice. All right. So that's almost it. Just as a last step, if you ever look at some code which is provided by someone else, you can actually optimize this part. So I'm just going to copy this, and then I can rename this as lookAt2, and then let's here just see what we can optimize, right? So we can probably optimize this dot product. So I can say not dot product. This part we can optimize with dot product, right? It works because right? Because you would in here if you multiply both matrices. So we're going to get rid of this multiplication as well. So we're not going to need that at all. So we can just say here, lookAt, and then return lookAt. So we can optimize it here. So if we do dot, and here it's dot of what? Of our I, and dot of our right vector, right? This is going to work, and I define it in vector 3 actually. So we need dot of that. So here it's a dot of I and up, and here it's vector 3 dot of forward and up, and it needs to be negative, right? Because we actually need negative I. So we can do that. We can transpose this part, right? So to undo those rotations, so we can say right here, we just change this y and z. So here it was up x, and then we had up z here, and forward finally. So we need here forward x, forward y. We can get rid of this translation. Okay, it's actually going in reverse. That's kind of interesting. Let's see. Yeah, because here it's up. It's probably because of that. It cannot be up. It must be I and forward. Okay, now it works. I hope so. So let's just try with lookAt2. Yeah, the animation kind of looks the same. Yeah, it is. So we're good. Okay, just to explain it quickly. So basically you can pre-multiply some stuff so that you can avoid this matrix multiply and this transpose part, right? Because you can just transpose here when you define a matrix, and then here with a bit of a dot you can avoid matrix multiplication. So you usually, if you take a look at someone else's code, or you find some lookAt matrix on the GitHub or somewhere, you're probably going to see this optimized. Basically the code is going to be optimized and look something like this. Okay, finally that's it regarding lookAt and the view matrix. Hopefully you understood this. It's kinda hard, but at the same time it's also not. It kinda looks a bit weird if you see it the first part, but once you do the math you're going to understand it. So that's it for this video. In the next video we're going to clean this up because this is a mess right now, and I want to set up scene in such a way that we can actually work on lighting, because that's going to be interesting. And also we're going to define the pedals, and then we can finally start working on a game a bit. So that's it for this video. If you liked it, please like, subscribe, and until next time.